So in the second half of this tutorial, we're going to pick up where we left off and discuss angular acceleration related to the two other types of accelerations we know that can happen with an object, linear and centripetal. Okay, so when you're on a moving wheel or rim, all three could be happening at once, and you got to make sure we can distinguish between them. On top of that, once we have our whole angular acceleration, we can combine it with our knowledge of angular velocity, angular displacement, and time to come up with our kinematic equations. They're the same equations as we had before for velocity, time, acceleration, and linear displacement, except that they're going to be in terms of theta, omega, and alpha. Okay, so let's introduce the concept of angular acceleration, alpha. And as one might expect, if you remember what angular velocity is a rate of change of angular velocity. So let's take a look at again, this wheel, if you will. It could be a wheel that's free to rotate around the ground, or perhaps it is rotating about an axis right here. It doesn't really matter, and I'll demonstrate tomorrow. So there's three accelerations we can look at. So let's start with the two that we're more familiar with. It could be accelerating along the tangent line there. In other words, the speed v could be going up and up and up and up. Let's pretend we have a motor and we turn on a fan blade. Initially the fan's not moving with any linear velocity, and it goes round and round and round. It gains speed until it hits a maximum speed. So there would be a tangential acceleration. Because it's moving in a circle, a point on that fan is not only going faster and faster along the tangent, it is also accelerating inwards centripetally. Okay, that's just due to its changing direction, whereas a tangential is simply just due to change in speed. The third thing, the alpha we can get, is if it's gaining angular speed by spinning faster and faster and faster. Okay, so whereas if a wheel is going faster and faster, we can talk about angular speed versus tangential speed. We can talk about a corresponding angular acceleration for how quickly the radians are picking up the rate. All right, so the equation for angular acceleration is very straightforward. If a linear acceleration is the rate of change of velocity, angular acceleration is the rate of change of angular speed. Okay, and that's going to be radians per second squared. Now, I mentioned the other one, so let's formalize a little bit. Besides angular acceleration, one must consider tangential acceleration. That's just our fancy word for the linear one. But on this diagram, it's tangent to the circle. And then there is radial accelerations. Radial means along the radius. We call this centripetal. Okay? But for right now, we're just going to give the subscript a sub r. They're the same thing. So let's make a connection between linear acceleration and angular acceleration. It's a very simple connection. If linear acceleration is by definition delta v over t, and we learned that the connection between linear and angular is omega r, then we can see if we put in delta omega r, I'll do it over here. So a is going to be omega r, the change in that, all over t, and delta omega over t is angular acceleration, so that simply becomes alpha r. Okay, we saw before earlier that linear velocity is omega r, so now we see linear acceleration is angular acceleration times r, or we can rearrange that and say alpha is a over r. So that has its advantages of knowing at other times. Another derivation we can do, very, very simple, is we can relate centripetal acceleration to angular velocity. We already know that the centripetal acceleration is v squared over r. Okay, but we also know that v is omega r. So if we do the substitution, I'll do it off the side, we have omega r quantity squared divided by r, all right? And so we get, the final result is that centripetal acceleration is equal to omega squared times r. So that's a handy way of finding the centripetal acceleration. And if you want to get the overall acceleration back in a circle, let's say we are gaining speed linearly and we're still centripetally, we see those are perpendicular, so we can use Pythagorean theorem. Normally, in the last chapter, when we did centripetal, this was always 0, so acceleration was just centripetal acceleration. Now, we should be aware that you can get a combination of the two. So let's finish up by doing a problem where we use all our kinematics. So I've got a carousel, so imagine we're looking from above, we're going around and around and around. Initially at rest, so omega naught is 0. All right, constant angular acceleration, The angular is important, so that's alpha. This angular acceleration is maintained, of course, that's t. And then an important piece of information that you might want to write in that I forgot to is that the radius of the carousel is 2.5 meters. So we're going to calculate 6 things using the combination of equations from here as well as from the previous lesson. So let's jump right into it. So what's angular velocity? So this is maybe a little bit unfamiliar to you, so just go back the old-fashioned way of listing what's given, what's asked for. I'm asking for angular velocity at some point after, so that's going to be just omega f. What do I know? I know omega, I know alpha, I know time, I know r. So like before, if I go to the equation above, I see that I can relate all those variables, or at least 4 of those variables, as alpha equals delta omega divided by time. Okay, so I'm going to rearrange this and solve for omega. Omega is omega naught plus alpha times time. This is 0, and angular acceleration is given as 0.06. I'm not going to put in units, times 8 seconds, and so that's going to be 0.48 radians per second. Okay, that's our final velocity. What's the linear velocity? Well, I'm going to label that as v, make sure I get everything lined up. And there's a lot of different ways you can do v. We know v is v naught plus at, but we don't know linear acceleration, but we do know angular. So anytime we have that, the most direct way of doing that is v is omega r. If I'm going this angular speed at that time, then my instantaneous tangential velocity is simply the angular times the radius. So that's pretty straightforward. 0.48 times 2.5 meters. Okay, and so we'll get 1.2 meters per second. You can work that out. All right, next question. Tangential acceleration. That's just A. There's a lot of different ways you could do it. I could say A equals delta V over T because we just found the final velocity. A more straightforward way, I think, is that it's going to be equal to alpha times r. Okay, you probably didn't think of this, but that's the most direct way to do it. Either way, you should get the same answer, and that's 0.15 meters per second squared. All right, radial acceleration. Don't let that throw you off. That's just centripetal acceleration. Again, you could do v squared over r, or you could relate it to what we've already learned, or we saw above. It's equal to omega squared times r. Okay? And if this is confusing you, these two equations, I would go back and convince yourself that v squared over r and omega squared r are the same thing. You just have more choices now how to approach problems, which is generally a good thing. So this is going to be 0.58 meters per second squared. So notice that we're getting this acceleration. Tangentially, we're getting that one. They're very different. So what's the overall acceleration? Okay, I don't really have a symbol for that. I'll call it sigma A. Well, that's going to be AR, or AC, I guess, plus AT. And those are vectors at a right angle. So magnitude-wise, it would be AC squared plus AT squared. Radical all that. Okay, you can put in numbers, and we see the overall acceleration is 0.60 meters per second squared. Okay, lastly, angular displacement and linear displacement. So we got to recognize the symbol for this so we can choose the right equation. That's theta. The only equation we have right now is theta equals S over R. Okay, and S is the linear displacement, which we don't know. So we want to use how angular displacement evolves in time. So we have an equation for that. You may not think at the top of your head, but if this corresponds to X, so actually, let me go back. I'll come back to F in a second. If I ask for linear displacement, that's X, let's say. Okay, I know we can call S, but I'm going to go X. We can say X equals V naught T plus 1/2 AT squared, right? So on the angular side, we would call X theta. That's going to equal omega T, right? We use the angular counterpart to this, omega naught T plus 1/2 alpha T squared. And that's one way I could do it. I could also say from here, X is average velocity times time. Excuse me, that should be multiplied by time. Okay, and I could also say here that omega is average angular velocity multiplied by time, where the average is the initial plus final divided by 2. And the same thing would work here. Okay, so what I want you to understand, especially in this last problem, is when we ask for how something evolves in time or distance, the angular equations are identical to the linear with the exception or with just different symbols. Anyway, if you want to work these out, theta turns out to be equal to 1.92 radians, and x, which can be, I don't even have to do this, I can just say it's theta r, turns out to be 4.8 meters. Okay, I know I went through these quickly. Solve these for yourself, convince yourself you can do it, and then we'll do more practice in class.